Hello, welcome back. We have just one last topic to really get into, and that is linear regression. In the past series, we were looking at correlation, determining whether or not two data sets had some linear relationship. But now that we've determined that they do, the question becomes, what does that relationship look like? How do we quantify that linear correlation? So to get there, let's back up just a little bit, make sure everyone's on board with determining whether or not two data sets have correlation, specifically linear correlation. The way we did that was we used technology. Please don't calculate R by hand. We used technology to calculate the correlation coefficient. And what we said last time was the further away from zero that coefficient is, the more apparent it becomes that those two sets are linearly correlated, right? R bounces between plus or minus 1, 0 being the worst case, there is no correlation whatsoever. If it gets closer and closer to 1, that means there's a very apparent linear relationship between your two variables. In the positive direction, right, an increase in one causes an increase in the other. And you can also get closer to -1, and that's fine too. That just means that if you increase one variable, you cause a decrease in the other. In both instances, whether you're close to 1 or close to -1, you can start to say that there is a linear relationship. Unfortunately, the eyeball test, just eyeballing it, gets increasingly impractical, especially for very large data sets. And so to get around that, we started bringing in the idea of hypothesis testing, where we took that R value we found and we also tossed in for good measure the size of the data set, so the sample size, the N value, and that would spit out for us ultimately a p-value. Of course, that p-value, which helps us reject or fail to reject the null hypothesis, really we got to also stress before we worry about the p-value what that null hypothesis is for our correlation check. Our null hypothesis for correlation is always R equals 0, which means the null hypothesis that we're always checking against is no correlation. So if we get a low p-value, specifically lower than alpha, we're able to reject that null hypothesis, which for us, if we're hoping for a linear correlation, is great news. Because rejecting that null hypothesis, rejecting R equaling 0, means we reject there not being correlation. And if you'll forgive me for saying that, this means there is not no correlation. So forget the double negative there. We're able to say there is correlation. And that's how we determined whether or not two data sets had a linear relationship. So the question becomes, well, how do I quantify that relationship? How do I actually turn that, yes, we are related on a line, into an actual literal line? Well, to answer that question, let's take a little bit of a trip down memory lane, right? The most frequently used linear equation is y equal mx plus b. Hello, old friend. Y is one of your variables, so that's one of the lists that you've got there, be it height or weight or ice cream, whatever you're looking for in one of your lists. X is, of course, the other list. So you've got a vertical list, a horizontal list, and usually, and this is just nomenclature, in a lot of math courses, X is considered to be the independent variable, Y is the dependent variable, but broadly speaking, for linear equations, there's interdependence, mathematically speaking. Traditionally, in statistics classes, we like to use the horizontal axis to be the variable you have either the most control over or the least control over. Like time might go on here, temperature might go on here. Usually the thing you have a lot of control over, or there's things that are very straightforward. It goes in the x-axis, and whatever depends on the first thing goes in the y-axis. But again, you can do it however you want. The bigger focus that we need is the slope, which is the steepness of the line, and the y-intercept, which is b, which is just where it hits the y-axis here. And just to play around with it here for the rest of this video, the higher the slope, the steeper the line. Negative slope, just like a negative R value, is just a downward trend. And then B just tells you where you hit that y-axis. So that's what our linear equation looks like. We've got y, we've got x. What's M and B?